Now we come on to a set of topics which we only cover at a high level, but are pretty important because they basically take that previous model and make it fuzzier by introducing probabilities and other ways to allow us to get both a ranking automatically, but more importantly, actually try to get the relevance because we're trying to focus on providing relevant documents, not documents that satisfy a particular mathematical structure. So the previous approach with the query method, we had the documents, which are in the space of words or terms. We had queries, which were formulae, which could have answers, and then the result was the set of the documents satisfying the query formula. And we had these very simple example documents. We could do queries such as the one here, step and, China and, taconod, or man, and that would have a particular result. So that's classic query logic. Now, let's start thinking about fuzzy indices. It's relatively obvious that not all index terms representing a document are equally important. That's why we remove things like A and for and the and but and stuff like that. But there are also things like synonyms as well, which are important. And also, we do actually count the number of times each term occurs in the document, and probably if a term occurs 50 times in the document, it has some greater weight. Because maybe that if you have the word Higgs in a document, it's probably 10 times. It's probably a document about the discovery of the Higgs particle and should be returned when you make that query. So we want to try to assign weights to terms in documents. And we're going to try to, obviously this is going to improve our retrieval algorithm. We're not going to use Boolean. Boolean by definition is 0 or 1. And we're defining documents by fuzzy sets of terms. But and so it's not that the terms are exactly in or out of a document, but that they have a probability of being in or out of a document. And then we'll get a better chance of getting actual relevance and a better chance of getting rankings. So one particular example of an idea that can be used is the so-called Jacquard index, which is trying to look at the correlations between two terms. Remember, terms are words. So if you have a term T and a term U, the Jacquard index is the number of documents containing both T and U, and the number of documents that occur either T or U. So this is the term-term correlation coefficient, and it's not exactly a correlation in that suppose two words are such that 99% of the documents contain neither of those words, then actually they're pretty correlated because they're only present in 1% of the documents. And the fact that only in that 1% actually makes the correlation with them quite high. However, if those two terms don't occur very often in the same document, then this Jacquard index will give you a low correlation. Remember, we're not dealing with the laws of nature here. So we are inventing reasonable ideas and trying to formulate solid mathematically well-defined methods, but they come from rather vague initial assumptions. Or actually, not even assumptions, because you have various fuzzy indices and various ways of doing fuzzy search. You just see which one works best. So here's some examples of the Jacquard index for our three documents: step, man, mankind, step, man, and China, step, and mankind. Then we see that for the first document, we have, by definition, the Jacquard index of when T and U are equal is 1. If we have step and man, 3 documents have step or man, 2 documents have step and man, so that's 0.67. Same with mankind. This document and this document are both have both step and mankind. This document just has step, so again that's 0.67. China is 0.33 because step is in 3, China's in 1. Mankind and China, there is no document with mankind and China, so that's the only actual 0 here. So that's the Jacquard coefficient. So we can now use the Jacquard index to calculate one particular form of a fuzzy index due to Ogawa. This is, look at this, is pretty old, over 20 years ago. So this obviously predated the web. And this fuzzy membership is every term T and every document D, there is a probability or membership degree attached to it, which is certainly going to be between 0 and 1. And because it's this thing here is positive, and this is a product of things which are at most 1, and this product here is less than 1. So this thing here is less than or equal to 1. So this is positive between 0 and 1, so W is positive between 0 and 1. So we look at this thing 1 minus CTU. It's the fraction of documents containing one of term T and term U, but not both. Notice that we're running this product over all terms in the document. In particular term here is the term, if T was in the document, then we have this product here running over T. 1 minus CTT is always 0, because remember CTT is always 1. We saw that on the previous slide. So WDT is 1 where the term is in D, but it's going to be some number typically between 0 and 1 when T is not in D. And so this allows you to give a highest value of W if a document has terms U which often which are correlated with T. Remember, that's why we thought of C as a correlation coefficient. And if we have lots of U's which are correlated, then those numbers here will be near 0. And when we have things near 0 in this product, then we're going to subtract a modest amount from W. So W is 1 minus a set product of things. Whenever T and U are correlated, this 1 minus CTU is going to be near 0, and therefore this total product is going to be small. So here's some examples for these 3 documents here and the 4 terms here. So we actually see in this new model, the WTD is never 0. In fact, the smallest is 0.33, which is China and document 3. And that's because China is only correlated with step in one document. And so through step, document 3 gets a link to China. Obviously, this will be much richer if you take a real sample with lots of documents. So there are many fuzzy models, and you have to calculate their weights. Obviously, this one we just went through is a non-trivial computation, and you also have to link that with a way of processing queries in a fuzzy fashion. And so you don't necessarily want these very precise queries. But I actually think most users don't use complicated, precise queries. They use simple queries which are string words together. And so this model where you have a fuzzy membership of words to documents is maxed okay to such simple queries. So this has the advantage of improving the uh, relevance of the response, because you're going to allow um, queries to to be linked to other words which are very importantly correlated with, like, if you query on George Bush, that's correlated with the White House or something like that, and vice versa. So there are some queries where you definitely want to look at related words which may not occur in a particular document, and you automatically will get a ranking.